Remember science class? You probably have that mental image locked in your head. Little particles jiggling faster and faster when things get hot. It's how we were all taught to understand thermal expansion. You know, why a bridge gets longer in the summer. It's simple, it's intuitive, but what if it's also just wrong? Let's dig in.
So here's the official story, the one you'll find in textbooks and on Wikipedia. It says temperature is just the average kinetic energy of molecules. You add heat, they start moving around more, vibrating like crazy, and they need more elbow room, so they push each other apart. And on the surface, yeah, that makes total sense.
But what if that neat and tidy story isn't the whole picture? What if the very foundation of that idea has a huge, gaping hole in it?
All right, so before we start poking holes in it, let's give the classic theory its due. Let's really quickly break down the idea that we all learned.
And this quote right here, it really gets to the heart of it. The idea is that heat equals motion. So more heat means more motion, and all that extra motion needs more space. It's kind of like a crowded dance floor. When the music gets faster and everyone starts dancing, the crowd naturally spreads out.
So the logic seems rock solid, right? It's a simple 1, 2, 3. Temperature is kinetic energy. That kinetic energy shows up as vibration, and more vibration forces everything to expand. Now, if this logic is sound, it should be true for everything. No exceptions allowed.
Yeah, but here's the thing about science. Exceptions are everything. They're not just little quirks, they're giant flashing signs telling you that you've missed a huge piece of the puzzle. And this theory, oh, it's got a whopper of an exception. You see, the jiggle theory makes one very clear, non-negotiable prediction. You add heat, volume goes up, always. But in the real world, that's just not true. Some things actually get smaller when you heat them up. It's called thermal contraction, and according to the old theory, this just shouldn't happen.
And you don't have to look far for the most famous rule breaker. It's just water. Take a look at this. Between 0 and 4 degrees Celsius, when you add heat to water, it doesn't expand. It shrinks. It actually gets denser. This is a huge problem for the old theory. It has no answer for this.
And listen, this isn't just a fun fact you pull out at a party. The source material is really clear on this. This is a direct contradiction. It's a signal that the whole logical chain we just talked about, it's broken somewhere.
And this crack, well, it leads us down a rabbit hole to an even bigger puzzle. It's not just about the size of things. It's about where all the energy we call heat is actually going.
Okay, to figure this out, we gotta talk about something called specific heat capacity. It sounds complicated, but it's not. All it is how much energy you have to pump into something to raise its temperature by 1 degree. Kind of like thermal inertia. Some things are just harder to heat up than others.
Now, here's where it gets really interesting. If that old theory is right, if temperature is only about kinetic energy, you can actually calculate what the specific heat should be for any gas. And for simple, single-atom gases like helium, the prediction is almost perfect, like spookily accurate. So far, so good.
But the second you look at a more complex molecule, the whole thing just collapses. For something like octane, gasoline, the theory is off by a jaw-dropping 93%. It can only account for 7% of the energy. So where is the other 93% of the energy going? It's like it just vanished. Okay, this is the aha moment. The researchers looked at this missing energy and they noticed something incredible. It wasn't random. The error lined up perfectly with one thing: the number of bonds in the molecule. The more bonds, the more missing energy. That's not a coincidence. That's a breadcrumb trail. And that trail leads us to a whole new way of thinking. The energy isn't just making things jiggle. It's going somewhere much more fundamental, inside the bonds themselves.
Okay, so here's the big idea from the source paper. They call it dynamic energy. And it basically says temperature isn't just jiggling, it's a combination of things. And you know what the biggest part is? Potential energy. It's energy that gets stored inside the atomic bonds. Think of them like tiny little springs. When you add heat, you're not just making them bounce around, you're stretching those springs.
So if all the energy is going into stretching these bond springs, where does the jiggling come from? Well, it turns out the jiggling is just a side effect. When a bond absorbs energy, say an electron jumps to a higher energy level, the atom itself actually gets a tiny bit bigger for a split second. And that sudden puff of expansion pushes on its neighbors. That push is what we perceive as kinetic energy, as vibration. The paper gives it a name: transimpact.
This image shows it perfectly. Look at A, you've got 2 atoms just hanging out. Then in B, the bottom atom absorbs some energy, and poof, it inflates, like a little balloon.
And the consequence, in C, is that it literally shoves the other atom away. That's the trans impact. The jiggling isn't the cause of expansion. It's the result of energy being stored in the bonds. It completely flips the script. All right, so let's put all the pieces together. Let's see how this bond energy theory doesn't just work, but it beautifully solves all the problems the old theory couldn't touch.
So the prediction from this new theory is incredibly simple and elegant. If expansion is all about storing energy in bonds, then it's simple. The more bonds you have, the more places you have to store energy, and the more you should expand. More bonds should equal more expansion.
And check this out. When you look at the actual data, it's a perfect match. You have water with just 2 bonds, pretty low expansion. Then propylene with 9 bonds, it expands more than twice as much. Then you get to gasoline with a whopping 25 bonds, and its expansion is way higher. The data lines up exactly with the prediction.
And what about that weird behavior of water, the thing that broke the old theory? Well, this new idea explains it perfectly. You see, when water is close to freezing, its special hydrogen bonds lock it into this kind of rigid, open lattice structure. It actually has a lot of empty space. So when you add a little bit of heat, from 0 to 4 degrees, you're not stretching bonds yet, you're just breaking that rigid structure. The whole thing collapses on itself, getting denser. That's your contraction. It's only after 4 degrees, when that structure is broken down, that the normal bond-stretching expansion starts to take over. Mystery solved.
So here's the big takeaway. That mental image we all have of thermal expansion, the little particles just jiggling around, needing more elbow room, it's not quite right. The real story is so much cooler. It's about energy being stored inside the very fabric of matter, in the bonds that hold our world together.
And that just leaves you wondering, right? If something we all learned in school, something as basic as this, was really an incomplete story, what else is out there? What other scientific facts are just waiting for someone to look a little closer and uncover a much deeper, more beautiful explanation?